So, okay, well, I'm glad that we're getting value out of it, though. So if people are watching it and finding it useful, we can do it. We're good to go? Okay, so let's get going today. And okay, so what are we going to talk about today? We're going to talk about computational models. I'm going to show you a little concept map to try to tell you where that fits in. But before that, let's go through a couple of public service announcements. And I mean, is this coming through on the microphone okay? Okay. So reading for next week, it's a longer one. It's chapter 5 of Reconfigurable Computing, this textbook that was written by DeHaan and Hauk. And it's on what we're talking about for the next couple of weeks. It's computational models. So computational models are basically, we can do anything we want on a piece of silicon, right? We can organize it in a huge number of ways, which can be overwhelming. So what are some models of computation people have come up with that help you organize your thoughts? You know, think about ways to organize computation. It's not like there's one that's right and another one that's wrong. Different ways of thinking. So read that, and it'll help you understand the next couple of lectures. I mean, my examples and the exact tack I take is related to, but not exactly the same as a textbook. So I think reading it is actually a useful complement to what we're talking about in lecture. So anyway, and then submit it. If you read it, submit a questionnaire before next class, and it'll count as one of your 10 questionnaires that you need to send in. Assignment 1 was released. It's due October 9th at the end of the day. And it's basically about optimizing a design, a relatively simple design, and trying it in a few different computational models. So we're using this as an example of, we're talking about a whole bunch of different computational models. Let's take a few of those, have you use them in this assignment, and see how efficient each one is. In terms of performance, in terms of area, in terms of power, how efficient are they? The side goal of this is make sure you understand how to use Quartus to implement a design and examine how it was implemented, how to use ModelSim to verify that your design works, and a refresher on just writing HDL. So on the UG machines, which you can log into in person here on campus or remotely using the VNC guide that I posted, you're going to use Q21 start. Okay, so that starts Quartus version 21. And the reason you want to use Quartus version 21 is that at least one student found, and I found the same thing, that the chip planner from the previous version of Quartus isn't stable with the new operating system that's on those machines. So Quartus 21 is the latest version. Use that command to start it. And ModelSim 18, which isn't the latest version, but actually doesn't need a license. So this comes back to that license issue. We're using ModelSim 18 because it basically does the same thing as the most recent version, which is a slightly newer, but not really much different. And this one's license works. And the system administrator is in discussions with Intel about trying to get a license for the latest one. But you don't really need it. So that's why we're starting with these two different ones. Yeah, do you have a question? Or are you just stretching? Okay, no problem. I was hoping for a question, but I'll accept the stretch too, because it's a sign of energy. So thank you. So the other thing you can do is install Quartus on your own machine. I generally tell people it's probably easier to use the UG machines because you don't have to worry about licensing. On the other hand, I did install Quartus on my machine and just said, forget about licensing. I just want the 30-day evaluation license, and it all seemed to do everything I wanted. So on your own machine seems it's not too hard either. Whatever you like. Okay, so concept map of what we're talking about. So last lecture, we were talking about, what are FPGAs? Why would we use them? What are they good at? How do they compare to ASICs, to processors? What we're talking about today is going further into how to use FPGAs. And really, it's actually more than just FPGAs. How do we organize hardware? But because you usually buy FPGAs because you want to make hardware, that's relevant here. So what are compute models, ways of organizing your system? And what are some of the pluses and minuses of different compute models? So this isn't about what's inside the FPGA, really. This is about how do we just design hardware in efficient ways. Okay, before we go to that, I'm going to share the course survey results with you. So most of you filled out the survey, which is great, so thanks. And I got to say, these Microsoft forms are pretty fancy. They just summarized all the information for me nicely, so I'm just going to show you the summary. Okay. Maybe I'll do this after the break then. Maybe I need to do this on my other machine. Okay. Let's see. You know what? At the break, I will figure this out. I think this means I need to log in. But so I'll show you the rest of this after the break. Let's turn off the projector. And okay, so I'm going to use the chalkboard for most of this. We'll go back to this after the break when I've had time to sort it out. Okay, so as I said, what we're talking about today is compute models. And that reconfigurable computing book that you're reading for this week is chapter 5, makes a distinction between compute models and system architectures. Now, these aren't exactly the same thing. A compute model is how do you think about a computation, and a system architecture is how you organize your hardware. But they are really kind of closely tied together. If you're thinking about the computation in a certain way, it usually strongly influences how do you design your hardware. So I'm going to kind of blend these together somewhat because I find the distinction is not 100% clear. Okay, but basically, the reconfig compute book, chapter 5, goes through this as well with a slightly related but slightly different take. So it's worth reading. Okay, so let's start with, we could make a really general compute model. Okay, so, and let's start with that. So, okay, so there's a really general computational model, whoops, get rid of that, called communicating sequential processes. Okay, let me draw what that means. Okay, so we have processes. Within a process, it kind of goes through sequentially, like a finite state machine or like a bunch of instructions in a program. So we've got a sequential process, just like a program or finite state machine. But we don't just have one of those. We have a bunch of them. Okay, so maybe 3 in my example. And they communicate. And they communicate with events. Okay, so this one can say, something's happened. I'm going to send an event to you. And now you can respond to that. And we can have a bunch of these events going between them. So it turns out you could describe, I don't know, actually I don't know if you can describe all computation with this, but certainly the vast majority. So you could have one sequential process, and that's just your program, right? The programs that you wrote in first-year undergrad, for example. You can have, these can each be, an always block in Verilog, and they're communicating through, the inputs and outputs of the blocks. So this also exactly describes the way basically Verilog and VHDL work at their most fundamental level. So it can describe, a very wide variety of computation. So it's very powerful. But it gives you very little guidance in how you organize anything. Because as I said, this is basically the Verilog or VHDL model. Just write a bunch of processes with a bunch of inputs and outputs to allow them to communicate. Doesn't tell you how to organize anything. Okay, so little guidance. In implementing or reasoning about a design. Okay, so while this is really general, and so if we were theoreticians, we might just say that's all we need, right? Like we want a general model that describes everything. But we're actually trying to implement, this is probably the wrong way to think. You generally want to use the most restrictive model you can. So the most restrictive compute or system model You can, okay? Okay, why? It organizes your thoughts more, and it tends to make your hardware more efficient, because restricting how things work lets you essentially simplify your hardware. So we're kind of going the opposite way of generality. You probably don't know this, but does anybody know who came up with this communicating sequential processes? Because the person won the Turing Award for it. So this was a big deal. Any ideas? Okay, there's no particular reason you'd know. It's Tony Hoare, who developed this, won the Turing Award, so computer science's highest prize. Anybody else know what else Tony Hoare came up with? So he's a pretty successful researcher, actually, right? So there's always somebody, if you think you're doing pretty well, you can always find lots of people where you go, wow, okay, well, I'm still not doing nearly as groundbreaking research as this person. So the other thing he came up with was, that he's famous for, is quicksort. Okay, so he came up with, well, typically the fastest sorting algorithm. So quite clever. Okay, so we don't want to use this really general model. I said we want to try to use, I mean, it's in the back of your mind. You go, I can describe pretty much all hardware, all programs with that, so that's useful. But now I want to go, well, what are more restrictive ones that I could try to implement? So one that we talked about last week is streaming data flow. And that's a really nice one for hardware. Okay, so streaming data flow we saw last week maps well to spatial hardware. And fundamentally, we've got a whole bunch of inputs. So a stream of inputs coming in. We register them. We can put them through some hardware block, say F, to make a stream of outputs. Put them through another hardware block, G, to further process them. So we saw we could compose spatial hardware. We register it again. And we also saw that we can make this faster by putting pipeline registers in the middle. Okay, so that was all good. Turns out that there are quite a few varieties of streaming data flow that people have come up with. So we're going to talk about these varieties, kind of going from the simplest and most restrictive to gradually basically less restrictive. But that doesn't always mean better. Less restrictive means you can map more computations to it, but it also tends to take more hardware. So again, the kind of good rule of thumb is if it's expressive enough for your hardware, use the simple one. If it's not, well, then use a more complicated one. Okay, so let's call this model A, and it's called single rate synchronous data flow. Okay, and exact names aren't super important. What's more important is just to remember, how are these models gradually getting more flexible? Okay, so in this model, your operators, so my operators here were F and G, things that transform my inputs to the output. So my operators don't change, they're static. Okay, so that's kind of nice for hardware. I just build them and they stay there. And then the other thing is that the data flows through all of them at the same rate. Okay, so the nice thing about this is it's very efficient in hardware. It's particularly efficient in FPGAs. And it's naturally pipelinable. So you can pipeline it more to increase parallelism and get more throughput. Okay, so let's say we have this operator F, and let's maybe look inside of it. Like we saw that we can compose this streaming hardware, this streaming spatial hardware. So if we look inside this, we can find submodules usually. So let's say our F looked like, we look in it, it's actually got some sub-operators. Okay, so that's what I've got inside of this. That's an input. Okay. And right now, it's not pipelined, right? We just wrote these operators to do what they should do, and there's no pipelining inside of it. So if I want to optimize this, probably the most powerful technique I can use is to pipeline it. So where? So where can I pipeline? Because I want to increase the parallelism. Okay, this is relevant to assignment 1 because one of the things you're asked to do is build a pipelined version of that computation. So we've actually given you a working version that doesn't have any pipelining. So if you can figure out how can I pipeline things with transformations that are guaranteed correct, you can optimize that design with pipelining without even really thinking about it too much. So yeah, what's the rule? We talked about it a bit last week. So let's see. Yeah. Right. Okay, so we have to add the same latency to every path from input to output. Okay, if we don't do that, basically our data doesn't line up anymore. Right? We'll be computing some of our intermediate values with things that are out of sequence. But if every path from input to output, we add the same amount of latency, it actually means that, well, our data is all still lined up at every operator internally. Okay, so that's right. Now it turns out that you can kind of simplify that a bit. So that's completely correct, and that's actually the fundamental constraint. This might be too vague. Does anybody know like how to operationalize that? You have any techniques that you've heard of that would say, okay, what can we do? This is a graph. What can we look for in this graph to find good places to pipeline that would meet that constraint, that would guarantee that we've added the same latency to every path? So we could do this kind of by hand, just kind of like trying things and checking the latency, and that'll work. But there are some shortcuts we can take where we're guaranteed that the following technique will keep the latency the same for all the paths. So any ideas? This might be kind of a vague, difficult question. So what do you think? So you're saying a symmetrical cut through the graph? Sorry, can you say that again? So you're looking for you said a symmetrical cut, is that right? Yeah, that's exactly right. So, so the fundamental rule, okay, so the fundamental, so basically all input to output paths must have their latency changed by the same amount. Okay, so in this example, there are no registers here, but if I had some registers, what I have to check is that the amount of latency I've added to every path is basically the same. Okay, if I add some latency to some input to output paths, like one cycle, I better add it to all input to output paths. But that can be simplified down to make a directed graph, which is what I've done here, of the operations that you're doing, and find a directed cut. Okay, that divides inputs from outputs. And adds the same latency to all these I/O paths. Okay, so maybe I don't want to do that. So let's see. Okay, so I said I want a directed cut. So let's say I do this one. So I take that cut, and what that cut implies is everywhere this cut goes through an edge, I would have to put a register. Okay, so I put a register there, I would put a register here, and I would put a register there. Okay, so this cut would imply 3 registers. And is it okay? Okay, so does it disconnect my inputs from my outputs? Like, is it actually a cut? What do you think? Can I get from input to output without going through this cut? What do you think? Did it actually cut my inputs from my outputs or not? Yeah, so I see you nodding your head. So it did. I can't find any path that doesn't go through this cut. So it is a cut, right? It cut my inputs from my outputs. The other thing is that it's a directed cut. Basically, it's important that all my edges cross it in the same direction. Okay, so this is crossing my cut from left to right. This is crossing the cut in the same direction. This is crossing the cut in the same direction. And that's important to make sure that I'm actually adding the same latency. I'm going through the cut in the same direction each way. Okay, so let me write that down. Let's see here. Oops. Okay, so all my edges well, I should really say cross the cut. That's probably not quite the right way to say that. Okay, so I've disconnected my inputs to the outputs, and I'm always got input on one side of the cut and output on the other side. So I'm always crossing in the same direction. And yeah, that is a legal cut. Let's see. Let me draw another one. So I'm going to draw this again. So this one would be okay. Let's see. So would this be right? Put a register there and put a register there. What do you think? So you think it's okay? Does everybody think it's okay? So it is a Oh, wait a second. I have one more path. That one actually would be okay. I forgot to put that edge in. Okay, so now that I put that edge in, does that change your answer? So what do you think? So it's not okay? Yeah, I mean, if I try to draw a cut through here, it's like, where is my cut? I can't really draw a cut through there without cutting this one too. I didn't put a register on there though. So I do have a problem here. And if I take a look at latency, let's take this path. This path going through this, down here and through there, I've just added 2 registers to. But I could also take this path, and that path I've only added 1 register to. Okay, so I violated my fundamental constraint of I'm supposed to add the same latency to every input to output path. I failed that constraint. In terms of my cut constraint, well, I didn't actually make a cut, right? Just putting a register there and register there doesn't disconnect my inputs from my outputs, right? There are still, let's see, well, can go from there to there. I can go from there to there. And let's see. Well, I failed the latency constraint. I'm trying to figure out if I actually failed the cut constraint as well. So I for sure failed my fundamental constraint. I'm trying to figure out, is there any way that I could get from input to output with just a cut that cut those 2 edges? And I guess I can't make it all the way to the output, but I still fail my latency constraint. Okay, so that is your fundamental one. So it has to be a cut, but then also check that your latency matches. Okay? So the directionality, this one's going from the input side to the output side. This one's going from the input side to the output side. So I guess I'm okay on directionality. And I did make sure I can't get from there. And I can't get through this path to the output. I can't get through this path to the output. So it is actually disconnecting my inputs from the outputs, but it still fails my latency constraint. Okay, so you still want to check that one. So this one is not okay. Okay? Okay, so you want a directed cut, but then still check for this latency constraint. Okay, so what do we want in our cuts? So in general, you can actually make a lot of cuts. So this one was illegal. It's not going to work. But I can make lots of other ones that are legal. So let's see. Let me erase this. And I could have done a cut that went like this. Okay? And that's fine. Is that cut, as good as this cut? So, I have lots of places that I could pipeline. This is legal. I've added the same latency to every input to output path. And I've disconnected my inputs from the outputs. Or I could do that one. So what do we want in our cuts? We could make a lot of cuts, but they're not all equally good when we're pipelining. So what do you think? So what kinds of things would you like in these cuts? We're trying to make the circuit go faster, and we're trying not to add too much area. Okay, now flip-flops are relatively cheap, especially in FPGA, so we're not adding huge amounts, but they're still not free. So we'd rather not add more than we have to. Okay, so our clock frequency is always limited by the longest path between 2 registers. So what do you think? What kind of cuts are you looking for? Yeah, so you'd actually like to divide things, basically equal logic on both sides. Okay, so this will be hard to achieve, but if you perfectly divide all of your paths, you double your clock frequency. Now, usually you can't quite do that, but the closer you are to it, the more impact from your pipelining. So that's good. So that's one of the things you want to do. Anything else you'd like to do? So this circuit's kind of too simple to see many other options. But yeah, what do you think? Do you say cut as many edges as possible or cut as few as possible? What do you think? So I'd say it's, okay, so what does okay, what happens when we cut an edge? So we cut these edges. And let me make this actually a little more, let me see if I can make this more interesting or not. Okay, let's say I have this. Let's say I put another F5 here. Okay, and then it goes to there. So I can make my cut here, and I'll get 3 registers because I cut 3 edges. Every edge that I cut, I got to put a register on. Does that make sense? But I do manage to get rid of this logic from my critical path. My paths get shorter because F1 is kind of taken out of the picture, right? My longest path will be through here. Okay, so that's one option. But I could also go here. So I could put a cut there. If I put a cut there, I cross 2 edges. Okay? So does that affect your answer? Because this basically cuts F4 off of my paths. So let's say F4 and F1 are about the same delay. I got about the same delay benefit. This pipelining got rid of F1 from my critical path. This pipelining got rid of F4 from my critical path. But this one I had to put in 3 registers, or these actually might not be single bit. They might be buses. So this might be 32-bit numbers. So this actually might be 96 registers. That's more common. And this might be 64 registers instead, if there are 32-bit buses. So cutting fewer edges means I put fewer registers in. So what do you think? Do you now like cutting fewer? Yeah, so cutting fewer, basically with few edges cut. And that basically means fewer registers. Okay, so yeah, as you look for cuts, that's your first goal is usually try to balance the logic on both sides. And then your second goal is if you can find spots where you're not cutting as many edges, those are actually efficient. They're not going to cost you as many registers. All right, so let's talk about loops. Okay, so let me draw a little streaming circuit with a loop in it. Okay, so I've got this circuit, and these were what are called feed-forward circuits, right? The data flows from input to output. This is no longer a feed-forward circuit. It's actually got a loop in it. So my old output affects, my later outputs. So the one on top might be what's called a finite impulse response filter in signal processing. That's actually your output is only a function of your current input and some older inputs. And this might be an infinite impulse response filter where actually your output's a function of previous outputs. Or maybe it's a finite state machine. But it's got a loop in it. So does somebody have a question? Yeah.
I have a question about the cuts. Can you explain also, do it have to be, you had an example where you didn't cut through the middle, and that was still a cut.
You have to, okay, so you have to disconnect the inputs from the outputs. Okay, if you don't disconnect the inputs from the outputs, it's not valid. Okay, you do. It has to be a directed cut. All the edges have to be flowing from one side to the other, like the input side to the output side. Okay, and there's still the occasional case where you wind up with a cut that disconnects the input and output, but your latencies still don't match. Okay, so and in that case, you still have to reject it. Yeah, it's basically, the case where I went like this and this, and I just said I'm going to cut those 2 edges, does not work. Because if I actually go and check if I have added the same latency to all paths, I haven't. And I haven't actually found a good way to explain why it doesn't work, except it doesn't match all the latencies.
We still go with the cutting thinking, or do we go with the latency thinking?
I guess, well, the latency one's the more fundamental one, okay? So latency is the fundamental rule. If you can match the latency of every pass, it is legal, okay? I guess the reason why this cut that I showed you here doesn't work is this is my input side, that's my output side. So I'm going across from input to output. This side is going from, what is this? This would have to be my output side back to my input side. And this would have to be my input side back to my output side. So it's not like a directed cut. I can't orient all the edges. Does that make sense? So when I drew this one, I couldn't orient all the edges from input side to output side. Does that make sense or not? Okay, so I actually have thought about this one some too, actually. So the latency constraint is the fundamental one, okay? But it's a lot easier to find cuts rather than to sort of check, does all the latency match? The one thing you got to watch for in cuts is it has to be like a directed cut. You have to be able to say this is the input side and that's the output side. Okay, so actually I think I've unconfused myself a little bit, so I'm going to take a short try at this. Okay, so let's take the cut that worked. Okay, this cut we said worked. Okay, and you can see it is a cut. Okay, it cut all the edges. There's no path that goes from input to output that doesn't go through it. And it's also directed. I can say I'm going from the input side to the output, from the input side to the output, and from the input side to the output. Right? It's always from this side to that side. So it's a directed, it's a consistent, which way am I going across the cut? If I did the cut the other way, like that, it's still a cut, but it's not consistent in which direction I'm going. I'm going from input to output on that spot. I just marked this as output. So now I'm going from output back to input side, and this would be input to output. So I can't kind of orient which way am I going across this. Does that make sense? Now that does get a little subtle, which is why I say, you can also go back to the fundamentals of did all my latencies match. Does that make sense? Yeah.
How to identify the output side and the input side, especially for a vertical one?
Yeah, so I guess you'd basically look at the first cut and go, well, am I closer to the input or the output? Okay, like on this one, it's pretty easy. This edge, I can reach this side of this edge from the inputs, but if I cut this, I can't reach it from the output. Okay, so this has to be input, this has to be output. Once I've marked this as output, then this side I've already marked as being the output side. Does that make sense? So I'm still connected to here, so this is still going to be the output side on this side of this edge. And I can say, well, from the input I can reach here. But then I get into problems, right? So now that I went from the output side to the input side. So it's basically like graph connectivity. Can I reach this point if I've cut this from the input side or from the output side? And it should be consistent, that the start point should always be reachable from the input side and the end point should always be reachable from the output side. And if it's not consistent, then your cut's not legal. Does that make sense? In most circuits, the nice thing is that you don't get weird patterns of edges going in odd directions, so that it's pretty clear where the input and the output is for a lot of feed-forward circuits. Like it's kind of obvious this is connected more to the input and this is connected more to the output. Does that make sense? And if you get really confused by it, then you can just go back to the latency one. But as I said, the cuts are kind of easier to work with. Okay, so we're going to put that one to bed for now. You can ask me in the break if there's more in it. I agree that it can get a little confusing about, well, is that a legal directed cut or not? Okay, so I've got this loop. Because what I had up there was feed forward, no loops, okay? This is not feed forward, has a loop. Can I pipeline it? okay? Because we love pipelining. Okay, when you see a long chain of lookup tables or multipliers or adders, you should feel sad, right? You should be like, they're only doing work for a part of my clock cycle. I feel bad about this. I want to pipeline it. So can I pipeline this? So I see some people shaking their heads. So why can't I pipeline it? Yeah, I can't, there's no legal place to cut it. I can't cut this in a way that maintains the same latency for all paths. And the easiest way I'd do this is kind of by contradiction. Let's say I just decide I'm going to try putting a register here. Okay, so I'll put a register is going to go on that spot. And if I do that, I've basically fundamentally changed the behavior of the circuit, and I can't fix it. You can't say, well, I'll put a register there, maybe I'll fix it by putting a register there. That doesn't make it any better. It just gets worse. So right now, my function here is y of I is equal to f2, this function, of f1, that function, of x of I. Okay, so one of its inputs is the current x value, and the old y value, y of I minus 1. Okay, so hopefully that's kind of clear. Current x, previous y go through F1, then we put them through F2. So that's just what I've written down here mathematically. If I put a register in here, fundamentally what I've done is I've added latency, okay? So that it now takes 2 cycles for my y value to get updated. So this is now going to be, y is basically going to be a function it's going to be f2 of f1 of x of I and y of I minus 2. Okay? If I put a register in there, I'm paying attention to too old a y. And there's no way I can fix it. If I put another register there saying, well, maybe that'll make some cut or make everything line up, it actually makes it worse. Okay? Now it's a function not of y of I minus 2, it's a function of y of I minus 3. And there's no such thing as like a negative register, so I can't make this work. Does that make sense? So loops are a pain. Loops can't be pipelined. So you try to avoid them in your speed critical hardware. All right, so I should write that down. So this is basically no pipeline. Okay, so that was all kind of the first subcompute model. So static, synchronous data flow. Or single rate static synchronous data flow. So we're going to make a slightly more general model called synchronous data flow. Okay, what does that mean? We got rid of the single rate. So why did I get rid of the single rate in the name? Sometimes we don't have the same amount of data at every part of our processing pipeline. Okay, so what if some operations so maybe some operations produce more output than input. Okay, I don't know. From signal processing, can you think of any simple example where you produce more output than input? And if you haven't done much signal processing, maybe this is a hard question. What's that? Yeah, averaging. Okay, so which in signal processing is often called an interpolation filter. But interpolation filter, a fancy way for saying averaging. Just stick a bunch more values in between the ones we have. Okay, so maybe data comes in at 100 million samples a second, but we decide we need more precision for some of our signal processing, so we average between pairs of samples and we convert it up to 200 million samples per second. So that's an interpolation filter. It fundamentally produces more output data than came in. Or we can have the other case. And an easy example of this is also from signal processing. You have things called decimation filters. Okay, so you might decide you have more data than you need. This part of the signal processing doesn't need to be that precise, so we're just going to drop every second sample. So we go from 200 million samples a second down to 100 million samples a second. And there's lots of other cases we can come up with more complicated algorithm where the amount of data they produce is different than their input. Okay, so but what does this mean? It means we can't run everything at the same rate. So the hardware I had before, data comes in every clock cycle, data comes out every clock cycle. It's kind of running in perfect lockstep. So what do I do if my algorithm doesn't do that, right? It doesn't produce a piece of data for every input piece of data. Okay, so that's our fundamental problem here. Can't run everything at the same rate. Okay, so, and there's a standard way to fix this, which is why there's a name for it. So what do you think? How would you, whoops, lost my mic, so the live stream's down. Can enjoy a break if you're remote. How would you fix this? What do you think? Sorry, go ahead. Multiple clocks? Yeah, you could do it with multiple clocks. That is true. It can get messy though. Right? So multiple clocks, you have to have clock crossing circuitry, more complicated timing analysis. You have a lot of these that can get messy, but it is a possible solution, you're right. Effectively, that's kind of like multi-rate synchronous data flow. You're like, let's keep single data rate, but we're not going to have just one data rate. We'll have a few clocks. So could do that, but not going to do that for this one. Any other thoughts? Yeah, what do you think in the back? Could you say it really loud? So same clock, but different clock enable. Yeah, so that's the right idea. How do I control that clock enable? So it's exactly the right idea, but like basically what's going to make that clock enable for me? Let me give you a... Yeah, it depends on the data rate. Okay, so let me give you a way that you might think of doing it. Make a finite state machine, and for this 200 megahertz versus 100 megahertz, count every second cycle. And you could do that. But as I make more complicated algorithms, your finite state machine is going to get really messy. And if I start trying to combine data from different sources at different rates, and sometimes there's gaps and so on, you might regret your finite state machine. Okay? So I like the enable idea. And I guess what I'm leading you towards is there anything I could do rather than just trying to write a lot of control logic to figure out when to enable things? Yeah. Sorry, go ahead. Data queue? Yeah. What does data queue mean?
So you're like, if the queue is not full, you put new data in.
Oh, okay. So you're saying to make a queue for the data. Yeah, okay. Yeah, that's a good idea. And that's actually heading towards kind of the next compute model. So save that idea. You're too far ahead. I have to slow you down. Amin, slow him down. But no, good idea. I'm going to come back to you. But for this one, basically, yeah. Well, you guys are on the right track. So I'm just going to write it down. Okay, so we can't run everything at the same rate. So what we're going to do is we're going to tag our data. So when you're writing control logic, the best way to make control logic, as much as you can, you try to like make distributed control, like kind of simple control that makes simple decisions on local data, rather than some big centralized state machine, because it's a lot easier to make, essentially local decisions and to compose these operators so that they kind of all fit together and it just works. So what we do for that is we use a data valid signal. Okay, so what that means is I got my F1, and it's already outputting data, but I'm now going to also have it output one extra bit, which is a valid bit. And my data is probably not 1 bit. Let's say this data is 32 bits, 64 bit, 128. It's pretty common in hardware designs that you're trying to be parallel, so this data can be pretty wide. So it's probably a lot more than 1 bit. You add 1 bit of just, are you valid or not? Okay, 0 means you're not valid, 1 means you are. And you do the same thing for, let's say you've got F2, another operator. So I put data invalid on it. That goes into some operator G. G basically will only process its inputs if they're both valid. Okay, so if these are both valid, it basically will output a valid signal. Otherwise, it's not going to output valid data. Okay, and I can put registers on all this. So the nice thing about this is if I want to pipeline it, I decide I need more pipelining, I just pipeline my data and my valid together. Everything stays in lockstep. It's all aligned. Their latency's lined up, and it all keeps working. So it's kind of a nice distributed control strategy. Okay, so this is called feed-forward control. That's another name for it. Lots of these techniques have multiple names. Okay, so in this case, G is going to execute when both inputs are valid. Okay, and you'd have to choose the speeds, like how, the clock rates of these things, so that you won't ever drop any data, okay? So you choose the speed of F1, F2, G, so that basically G can always keep up with F1 and F2, right? If this data is valid, then G has to produce an output. So you can never have G being slower, like at a lower clock rate or taking longer than F1 and F2. It has to be able to keep up. Okay, let's see. Okay, so this constraint can often be kind of hard to meet. To say that G can never, it always has to be able to process it fast enough. Okay, so there are cases where it can do that, but there are also cases where you go, I don't know how to guarantee that, right? Maybe G takes a variable time. Maybe there are cases where it's not going to be able to keep up with F1 and F2. So I think you already recognize that. Wait a sec, what if G can't keep up? Is that right?
As in, like, in this particular example, if F1, if the clock rate in F1 or F2 is differential, isn't it that we always lose some data?
Yeah, F1 and F2 are also going to pretty much have to be in lockstep.
Yeah.
You're right. Like in this case, if you said this is 100 megahertz, this is 200 megahertz, it's not going to work, right? Because F1 is going to produce data, F2 is going to produce data at a different rate. They both expect G to immediately process it, and there's no way for G to process at two different rates. So you're right. There are cases where this just isn't going to work. It's still not enough. Does that make sense? So valid bits are very useful. They help, but they don't solve all our problems. On the other hand, there are also actually some simple processing pipelines where you do know F1 and F2 are going to produce data at the same rate. So, and G can always produce an answer in 1 or 3 clock cycles, so it's going to be okay. So this does actually happen. But you're also right that as you get into the system level, you can wind up with cases where it isn't satisfied. Okay, so that leads us to our third variation on streaming, which is called by the reconfigurable computing book dynamic streaming data flow. And it's basically motivated by the things you've already flagged, right? Like, what if the time to produce some output varies? Whoops, sorry. It's getting a bit messy. Okay, so maybe G sometimes takes more time, sometimes takes less time. So that could be due to the algorithm you're using. Okay, so I'm going to see who remembers physics, or sorry, calculus. Does everybody remember what Newton-Raphson iteration is? Do you remember that term? It's an iterative approach to solve, like, what are the zeros of an equation, okay? Like, what are its roots? It's fundamentally iterative. So sometimes it gets it after like 3 iterations. Sometimes it gets an answer that's accurate enough after 10 iterations. So let's say that is inside my hardware. You know, I'm actually solving some equations and I'm doing it iteratively. Then I'm going to have variation in the time that G takes. Some inputs kind of are easy. Solve it in a few 3 iterations. Some are harder. So this is just an example. So it's just fundamental in the algorithm. Okay, if you don't remember what that is, doesn't really matter. But if it piques your curiosity, you can go back and do a Wikipedia search and remember first year calculus. It could be due to hardware, right? Could be memory latency. Okay, maybe G actually has to request data sometimes from external memory. And external memory, it varies in how long it takes for it to respond based on exactly where it is in the external memory. Is it in an active page? Is it not in an active page, et cetera? So you might have hardware reasons why this is changing. Also, you could have the amount of data varying. Okay. Do you guys remember what Huffman encoding is? Okay, so it's a compression technique, and it fundamentally assigns for common symbols in some set of data you're sending, it assigns short bit patterns, and for unusual symbols, it assigns long bit patterns, so it compresses. But that means the amount of data that you're sending, if let's say G or F, one of these things was a Huffman encoder, is going to vary, right? It's going to get some sequences that are easy to compress, and it doesn't send very many bits, and it's going to get some sequences that are hard to compress, and it sends a lot of bits. So it can be impossible to worst case this sometimes, where you just guarantee that this G operator can always deal with whatever rate these other two ones send it. And it can be impossible to line up the rates of F1 and F2 so that they're kind of in lockstep. So, or it could be extremely costly to worst case it. You could say, well, maybe I'll assume that it always takes 100 cycles because it'll never take more than that, but that might mean that you really slow down F1 and F2. way more than the average case would need. Okay, so maybe you can't worst case. Or maybe you don't want to worst case your throughput. You know, the amount of time it takes or the amount of data size it takes. Okay, so now it's time to go back to the comment earlier about FIFOs. Okay, so bring back that comment. What do you think? So one of the techniques we can use is FIFOs. We're going to convert some pipeline registers into FIFOs to decouple our operators. So let me take this down a bit. Let's see. Let's see if I erased my operators. Let's see. Yeah, so here I just had registers. So I'm pipelining this for speed. I can change these registers into FIFOs, so queues or buffers. And now I can deal with some imbalance in their rates. If this has a burst of data, it doesn't suddenly, this only can store one cycle's worth of data. Can't handle a burst if this doesn't take it out every cycle. If I put a queue in here or a FIFO, now I can handle a burst of data. Okay, so I can convert some pipeline registers to FIFOs. Okay, and basically that's decoupling the speed of my operators. Okay, so if I make a FIFO that's got 10 words in it, I can handle a burst, of an additional, 9 or 10 data words, and I'm okay. So I have decoupled my operators some, and if that's the biggest burst I'd ever get, the biggest imbalance I'd ever get, I'm fine. But in a lot of cases, we might not be able to bound this. Like these Huffman encoding cases that I gave you, maybe I get a whole bunch of symbols that don't compress very well, so I get a lot more data coming out of those early operators than average. And that happens for a while. So it's not clear how big to make my FIFOs for that. Like I can't make them infinitely big. If the imbalance persists for an unbounded period of time, I cannot make the FIFOs big enough to deal with it. So what do I do for that case? So FIFOs alone are enough if I know that I'm only going to get localized bursts and then everything's going to line up again. But the truth is that doesn't happen that often. Usually either things are perfectly lined up with like some of the simpler models we talked about earlier, or they're really just not lined up. You really can't give a lot of guarantees. So the interesting case here is I really can't bound how imbalanced the amount of data coming out of the first stage is versus the second stage. So what should I do? FIFOs is part of the answer, but it's not going to be enough because I can't make the FIFO infinitely big. So what else should I do? What do you think? Sorry, go ahead. Yeah, so I need some kind of handshake. So the name, it is a handshake, and it usually is called a back pressure signal. Okay, so usually we can't bound. Once we get into this case where we've got unbalanced amounts of data flowing around, we usually can't bound the computation imbalance or the data imbalance. Okay, so that's the common case. So what we need to do then is add back pressure signals. Okay. And so let me draw what that looks like. So And you're going to see, like, this computation model is a bit more complicated. You're going to see my diagram's a bit bigger because the hardware is getting bigger, which is why you don't want to use this if you didn't need to. It's not a bad computation model, but it is going to cost us something versus our simpler ones. Okay, so we've got our F1 operator. It goes in, it's sending its data. And its data still got, it's got data and it's got valid. Okay, so we're still able to mark, do we have valid data or not? But instead of going straight into our next operator, G, it first goes into a FIFO. Okay, so we can store some number of data words. And our F2 looks the same. Okay, it goes into a FIFO. Goes into G. Okay, G outputs, when it gets 2 valid pieces of data, takes them out of each FIFO, computes an output, and it puts that in another FIFO, which goes to, you know, whatever downstream. Okay? So what I've drawn is the FIFOs. I haven't drawn the back pressure yet. So I need to have a little bit of logic that's monitoring this FIFO. Whoops. And basically can send a stall signal. Okay, so this could be coded as either a ready signal, which means you can send me more data, or as a stall signal saying don't send me. It doesn't really matter, just the logical negation of each other. And I need that from every FIFO here. So this FIFO also has a back pressure signal, and this FIFO also has a back pressure signal. Does that make sense? So when should I assert this back pressure signal? Like when the FIFO's full? Yeah, usually, I mean, I should for sure do it when the FIFO's full, but normally you actually have to do it a little bit before that. Okay? So this back pressure signal is really like nearly full. Okay? Why is it nearly full? Well, it's basically got to cover the latency to stop this thing from producing more data. And that depends on how long it takes it to stop. So if you had no registers in this path, or, well, usually you're going to have at least one register, right? There'll be a register at the start of this. So if there was just one register, then it would be okay to activate this back pressure signal when you've only got one entry left in the FIFO. Now that could be speed limiting. So you might actually wind up putting registers on this back pressure signal. And inside F1, it might be pipelined. You know, it might have a bunch of pipeline registers, which are just basic pipeline registers. You know, you can't stop them. So if it's got 3 cycles of pipeline registers, you basically want to take how long does it take you to make this stop producing data, and you want to produce this back pressure signal that many cycles in advance. Does that make sense? So yeah, it's a nearly full, and you have to look at your logic and how deeply you've pipelined things to decide how many cycles in advance to have to stop it. Does that make sense? Does this work to compose? So one of the things you want to do with these compute models is we don't want to just build one block of hardware and say we're done. We want to have models where if we build a bunch of blocks of hardware using that model, we can put them together and they just work, right? That's one of the powerful things about, well, software, for example, and streaming hardware, et cetera. So can I put these things together and they work? In other words, let's say G starts filling up its FIFO because whatever down here is not taking data very quickly. Does this whole system work? Do F and F1 and F2, do they actually properly stop producing data so that they don't overflow their FIFOs and lose data? So what do you think? Look at this and see, essentially, is it composable? When I put bigger and bigger hardware units together, if they all use this style, do they just work? So what do you think? This could be like one of those ones where you could just do this. You can do this as sort of psychologically, too. You could say, well, is the professor going to ask this question if he's going to say, no, it doesn't work, I just wasted my time, right? Sometimes you can take a risk and you can say, well, I don't think he thinks that, but I think he's wrong. I'm just going to go for it. So that's fine. I respect that. Or you could go with, I think he means he's going to say it works. So what do you think? What do you think?
I think yes, it would work because when the cycle is nearly full after G and it applies back pressure to G, that slows down G, and that in turn causes the
Yeah. Yeah, so I'm just going to repeat that for those who didn't write it, couldn't hear it. But yeah, it all works. If G, for example, is being held up by whatever's down here, then its FIFO will fill up, it will be back pressured, it will stop accepting data from these two FIFOs. These FIFOs will gradually fill up. When they're almost full, F1 and F2 will stop. They will basically stop putting data in here. And that will gradually fill up the FIFOs that feed them, and the hardware that feeds them will stop if necessary. So if you use this throughout your whole system, the back pressure will propagate and stop the whole system if it has to. Does that make sense? The fact that we've marked valid on this, so it's also important that we have valid signals, that's handling the case of, maybe F1 is really not doing a very good job here. So it's slowing down G, right? So G is looking at this FIFO a lot of the time and finding there's nothing valid. So it doesn't do anything. And it tells the down logic, well, it doesn't put anything in its FIFO, right? So the downstream logic that reads its FIFO can also see, well, there's nothing for me to process. So it works both ways, right? If G's bottlenecking you, it'll slow down its inputs. If these inputs are not producing data that fast, the fact that they're not marking their data as valid in the FIFO tells G I've got nothing to do, right? And all the downstream logic will slow down. Yeah?
Or I think we can apply a different approach, like star scheme. Like we can have a message sender, like one people is almost full, and they send a message sender.
Okay.
Tell all the people that stuff.
So you're saying, so let me repeat that. So you're saying we could also have like kind of a central controller that's looking like what's going on everywhere and decides who you stop and so on. You could do that, but it's much harder to write and to scale and to compose. So the nice thing about this is it's often called distributed, a distributed control scheme, and it's also called a latency insensitive pipeline. Okay, so it's given lots of names. Distributed control is nice because the control is not that complicated. There's just a little bit of control logic added to every single operator, and then you put them together and they just work. If you start taking data out of a bunch of these operators and sending them to some central controller, that central controller usually gets quite complicated and quite difficult to decide how to add things to it. Does that make sense?
I think we can also have distributed standard controllers, like one controller only control a bunch of a small amount of
Yeah. Yeah, so there is a little bit of control in each of these. Like this G has to check, do I have a valid data word in the top of the FIFO from each of these? If I do, compute an output and put it in my FIFO, if there's room. So they do have a little bit of logic. If there's no room, I need to say I'm not ready. If there's no valid data, I need to not produce an output. But basically the logic is relatively simple and relatively repetitive that you can just do all over the place. Does that make sense? And the other thing is you can mix these models. These streaming models can be mixed. So a common one would be, let's say this G, I don't know, is like it's some floating point unit. It's doing a floating point dot product. So it's got a whole bunch of floating point numbers to multiply and then add up. So if all of its inputs are ready, it could be guaranteed in 30 cycles it's going to produce its output. Like no question, right? It's producing a dot product every single time. So you can still use, and you often do, like just simple pipeline registers inside this operator, for example. Okay, so inside this operation, I may know, look, my inputs are ready. I'm for sure producing exactly one output or 10 outputs or whatever. No questions, it'll take me 30 cycles. It's a lot more efficient then to just use simple pipeline registers inside of this. So it's using one of the simpler streaming models without any back pressure. And then on the larger operators where you can't make those kind of guarantees, you put in these FIFOs and so on. Does that make sense? Okay, let's see if there's anything else to say about that. Okay, I'll say a few more words about this and then we'll take a break. How do you build one of these FIFOs? Okay, so I told you registers are pretty cheap in hardware. They're actually not as cheap in ASICs, but they're very cheap in FPGAs relative to other things. And they're not that crazy expensive in ASICs. So let me just erase this for a second. Okay, so registers, pretty cheap compared to most of our operators. What about FIFOs? What do you think?
Sorry, could you explain a bit why we want to pipeline register inside?
So why do I pipeline inside G? Okay, so let's say G is a complicated unit. Okay, let's say it's a floating point dot product unit. Takes in, I don't know, 2 vectors, each of 10 numbers. Multiplies the vectors together, add them all up. Sorry. So you don't want to do that in one cycle, right? That's a lot of work. So I might do that in maybe 30 cycles. And if I'm going to do it in 30 cycles, I need 30 pipeline stages. Okay, so I can clock it fast. I would much rather do that. It's going to be much cheaper if I do that with 30 sets of actual registers than if I do it with 30 sets of FIFOs with back pressure signals. Does that make sense? So it'll be much cheaper. And inside G, I know, I built G, for example. Let's say, okay, I'm the engineer building G. I know that I do not start the computation till I have both vectors. Maybe each of these is producing a 10-element floating point vector and a data valid bit on it. I don't start the computation until I've got both ready. Once I start that computation, it's producing one floating point number 30 cycles later. There is no reason for me to use a whole bunch of FIFOs and back pressure signals inside because I know exactly how much data is going to be produced. I don't need back pressure. I don't need anything. Does that make sense? I still want a valid bit because maybe I had nothing to do. So my output should still, I got to carry a valid bit through or have a little bit of control logic to mark the valid bit on 30 cycles later, one or the other. But to be honest, it's often easier to just send the valid bit into a 30-element shift register, have it just travel along with the data. And it's much, much cheaper. Does that make sense? So as an example, we're mixing compute models where we don't need the extra power of this when we don't use it because it's not free. Does it make sense? Okay, so yeah, how do I build these FIFOs? So just give some sense of what did this cost. I said pipeline registers are pretty cheap. How expensive is a FIFO? And to answer that, it's kind of like how do we build it? So what do you think? How do we build a FIFO? Yeah, so there's actually 2 basic ways to build them. So one basic way to build it is a shift register. So let's say my data is not 1 bit, because 1-bit data is usually not that realistic. So let's say it's 32 bits plus 1 valid. Okay, so 33 bits. And let's say in my FIFO I decide that I need it to be 5 words deep because I need a few cycles to send the back pressure signal back and stop the previous thing. So maybe I need 5 words, and each of them are 33 bits. And I could do that, with a bunch of registers in a shift register. Okay, and these shift registers have to have an enable signal so that I can stop them. Does that make sense? And I also need a little bit of logic to figure out when they're full. Okay, so I'm going to have to write a little bit of logic to say, are you full? Is there nothing here? I can look at the valid bits, and I can figure out if this thing is full or empty or not. Okay, so I need that too. So that's one way we could build a FIFO. And it's not bad as long as I don't have too many registers. Okay, so if I only, this one's already getting a bit bad. Okay, so 33 bits times 5 words. That's like something like 160 registers, 165 registers. That's actually getting reasonably large. I said that registers are pretty cheap in FPGAs, but this is now getting to be a reasonable number of registers. And well, maybe I don't need 5 words, maybe I need 10. Okay, so if I need 10, now I've got like 330 registers. So this can get relatively large. It's also pretty high power. Every time a new piece of data comes in, everybody shifts over by one. Okay, and power in all modern circuitries, which is CMOS, primarily occurs when you change data because you're charging and discharging capacitance. So this is a high power solution because, well, you have a lot of registers, and when you have new data, they all change. Okay, everybody moves down one. That's a whole bunch of capacitance charging and discharging. It's called a high activity. So it's fine if you don't need very many registers. So the data bus is narrow and you don't need many words, but as you get bigger, it's not great. Yeah?
But doesn't it mean you can only read when the line is full? Like when you propagate all the way to the end?
That's true. Yeah, so what you would have to do as well is you would have to probably put a multiplexer on this to allow you to select which one to take out. Does that make sense? So you either have to, I mean, that's the easiest way to do it. So you basically can read out whatever's at the head of your shift register, whatever's the next valid word. There might be a way to do it as well with like deciding where to put the next one, but you're right, you need some muxing as well so that you can get the data out, which makes this a bit bigger still. So this is used for FIFOs if you don't need very many bits. But if you need more bits, either because your words are wide or you have many words, it's not a great solution. So what do you do as it gets bigger? Yeah. Sorry? Yeah, so as your FIFOs get bigger, and this will be the dominant thing. Most FIFOs are big enough. Like, they don't have to be all that big before this is more efficient. You basically put them in a RAM, and you have 2 pointers. So this is one. FPGAs, as I showed you, have tons of RAM blocks. So this doesn't have to be one RAM block, but you build it out of 1 or more RAM blocks. You don't really have to build it all yourself. If you describe it in HDL, the CAD tools will build it for you. But you basically have a RAM, and you write in words into the RAM, and you keep a write pointer. Okay, so that's in registers. It says what's the address of the next free spot for you to write into. And you have a read pointer, which is what is the address of the oldest data that I haven't taken out yet. So you need, a few registers to store these pointers. You need a little bit of logic to update them. Yeah, that's basically it. This becomes, you still have to store, you have to have an SRAM cell in this RAM for every piece of data you want to store. So if I had 33 bits of data times 5 words, I still need to have 165 SRAM cells in here. But 165 SRAM cells is actually significantly smaller than 165 registers and all of the programmable routing that is used to connect to them. Because an FPGA is not just the registers, there's also programmable routing to let you talk to it. So this becomes a more efficient solution as your FIFOs get bigger. And like I said, they don't have to be very big before this is more efficient. It's also, well, let me ask you this question. Which of these do you think is going to be lower power? Because power matters too. Yeah, so the RAM is lower power as long as it's not an extremely small FIFO. Okay, if it's an extremely small FIFO, then fine. The shift register might be smaller. The RAM is lower power because when you want to put a new data word in, you just write 1 word of the RAM. Okay, and when you want to read out a data word, you read 1 word of the RAM, and you change the read pointer to point to the next element. So that does take a moderate amount of power, but basically the shift register is worse because everybody's moving over 1. Okay, so it's like all the intermediate words are changing. They're all moving over 1. The RAM doesn't do that. You put it in 1 spot in the RAM, you leave it there till it is taken out. Only these pointers move around. And these are circular pointers. So when your read pointer gets to the end of the RAM, it wraps around back to the beginning. Okay? When your write pointer gets to the end of the RAM, it wraps back to the beginning. If your write pointer is ever about to cross your read pointer, that's when you say my FIFO is full. Okay? So in fact, you shouldn't check for that. You should check that my write pointer is within, say, 4 words of my read pointer, and I know I need 4 cycles for my logic before me to properly stop. Then that's the logic you write for almost full. Does that make sense? Again, you don't have to write all this yourself. inside Cordis, there are like IP cores that will also do this for you. So you can't just say, just give me a FIFO, okay? And Cordis will actually decide, based on the size of the FIFO that you want to make, whether to make it out of registers or make it out of RAM blocks. So some of this is abstracted a bit from you. Yeah?
So for the shift register implementation, like so for F1, like after 10 clock cycles, I think the data will shift out.
Yeah, the data would shift out. So you need an enable. So you need to be able to stop it if the data is not valid. Does that make sense? So it has to be a shift register with enables. And actually, as someone at the back said, it actually also has to have a mux, because when the shift register is not full, you still might want to take some data out of it. So you either need a mux or you need to write somewhat clever control logic or startup logic, but you need to do a bit more. Does that make sense? I have to think about, those mux is kind of annoying, so it's kind of like a puzzle of, is there any way to get rid of it by thinking about your startup logic or something? But I'm not sure if there is a way to get rid of it. So anyway, this is what happens as it gets bigger. But this is still significantly bigger than just building, one stage of pipeline registers, which is why we try to use those mixed approaches when we can. If we know it's not going to stall, just use regular pipeline registers. And then the bigger operators where we don't know that, use this back pressure and FIFOs. Does that make sense? Okay, so we'll take a break there. These are key hardware compute models. So these are really important ones to understand. Let's take a break until, it's 5:44, so we kind of went late. Let's say till 5:55. Get 11 minutes as a bonus instead of 10. So. Sure.
I'm not enrolling in this course, but I would like to after this today's lecture, and I'm thinking about whether I have missed any past due or like.
Yeah, like basically if you have like operator G is complicated, you want it pipelined.
Oh, okay, that's
right.
yeah. This is why I'm confused because here we add a FIFO and the back pressure signal to solve this specific problem.
Yeah.
Right. So does adding pipelines inside the G
It's
also solve that problem?
Well, it's kind of, this is sometimes called an elastic pipeline, okay? Like where you have the FIFOs. It's basically where you have like, usually it's like relatively big units.
Yeah.
Relatively big units where you can't make many guarantees of, that they're always going to be ready, et cetera.
Yeah.
So, but you'd still like to combine them together and have them processing at the same time. So by doing this, you get what's called an elastic pipeline. You still get overlap of computation, but they can deal with computation imbalances. industrial perspectives. In terms of where you're coming from, this word chart shows a bunch of people from Intel. AMD is not listed here, but actually several from AMD as well. So from the former Xilinx probably. Cerebrus, which is another style of spatial computing for deep learning, everts who use FPGAs. So yeah, so I have to be, you guys can keep me honest, right? You can say, wait a sec, that's not the way we do it. You're totally wrong, so that's great. Research areas all over the map, with FPGA being the #1 keyword, but lots of other stuff about various types of hardware engineering and signal processing. Hardware description languages, there are a few who didn't select any, which is okay. If you don't know an HDL, you can pick it up. We don't expect huge amounts of HDL development in the course. It's more about optimization and as I said, doing comparisons between compute models. More people know Verilog and System Verilog. System Verilog is just the next generation of Verilog. I don't really know why they called it System Verilog. So if you're going, what is System Verilog? It kind of cleans up some Verilog syntax and gives some new features. If you know VHDL but not Verilog, don't worry, they're not very different, except syntactically. Can complete the assignments in VHDL, although I'd say it's a bit easier in Verilog because we wrote the test benches in Verilog. But either way, it's fine. Have you taken CAD for digital synthesis and layout? It's a 100% no, so I will not assume a CAD background on that. Professor Anderson, it's a very good course, by the way, so if you're looking for other courses in your degree, I'd recommend it. He's on sabbatical this year, so he's not teaching it, but it's a great course. I clearly will not assume anybody's familiar with the material. Do you know how to do digital design at the gates level? Most people. Do you know how to do digital design at the transistor level? Most people not, which is fine. We'll do some. When we get into the FPGA architecture part, you can't really talk about how efficient is it without having how efficient is the structure without thinking about how is it built. So we're going to build some of them with transistors, but I'm going to show you how to do that. It's not that hard. So don't worry about it if you're like, well, I haven't done transistor level design before. We're not going to be doing like advanced analog design. It's just, well, how would this be built so that we can estimate its area? Do you intend to attend class in person? Most people, which is great. But it seems like a few people are online, so seems like the feedback is people like having lecture videos, so we'll keep doing it unless we have catastrophic tech support issues that neither me nor I can take anymore, but I think that won't happen. And then I just like asking this. I just like trees, right? So I can't explain why, but we have like lots of trees in our property, and whenever we have an arborist out, I talk to the arborist for like half an hour. So when I retire, I'm going to become a park ranger. So I like to ask, what's your favorite tree? You can see a bunch of different responses here. This particular one, let me switch back to slides. And yeah, you can see that there's kind of engineering-y responses like binary tree, and then there's like more naturalist responses like ginkgo tree and oak tree and coconut tree. So the class divides up that way. And let me send the other slides to the projector. Okay, so let me switch back to this. And okay, so I did a slight amount of processing on this. So 77% of you put down real trees. 23, so pine, fruit, oak trees, etc. Ginkgo, sequoia, cedar, a few others. 23% of you put down engineering trees with variations on binary tree. And then somebody who's a unique perspective said, clock tree, which we'll actually talk about later in the course. Okay, so my favorite tree is the giant sequoia. In case you were wondering, you're filling out the survey, you're like, wait a sec, what is the prof's favorite tree? I want to copy that. In case you want to, it's giant sequoia. This is General Sherman. It's the world's largest tree, okay? And I know an odd number of statistics about it. I haven't actually gone to see this tree, but I'm going to sometime soon when I'm in California. Okay, so it's 3,000 years old. It's 275 feet tall. It's 37 feet diameter, and it weighs 4.2 billion pounds. Which is pretty amazing, actually. So if you go to, many of you are going to wind up going to conferences or jobs in Silicon Valley. So this is about 4 hours from Silicon Valley. In the Sierra Nevada mountains, so probably worth going to. Coast redwoods are closely related to giant sequoias. They're subspecies of, both subspecies of sequoia. So the coast redwoods are the tallest trees in the world. So their tallest one is 370 feet tall, which is amazingly tall. They're not quite as wide as this. And they're actually really easy to visit. So you can actually go visit coast redwoods just north of San Francisco. So, okay, so that's my unsolicited advertisement for sequoias. And you can tell me on the course evaluations whether that was like a 5 minutes of your life that you wish you had back. So, all right, so let me turn this off, and we're going to go back to chalkboard for a while. Okay, so let's see, where was I? Okay, so we kind of got through major streaming ones. We just talked about a few variations for the rest of the lecture. So we're not going to cover all compute models in this much detail. Like streaming hardware turns out to be really efficient, really nice for, well, hardware in general, FPGAs in particular. Okay, so a little more general still than what we looked at is what the reconfigurable computing book calls streaming data flow with allocation. All right, so what does that mean? Well, we've gradually gotten to more flexible hardware, but our operators are still fixed here. Okay, we've got an F1, an F2, a G, they never change. Do the same thing forever. In lots of hardware, that's perfectly fine. You're just repeating the same calculation. But in some hardware, it might not be ideal. Okay, so this means you can change the operators over time. Okay, and there's two basic ways you can do this in an FPGA. So method one's kind of maybe the more obvious one. Okay, so method one is just you build a more flexible operator. So you put some extra control in it. Okay. That's one way you can do it. Another technique in the same vein is just build muxing. Okay, so build multiple operators or multiple pieces of an operator. So build muxing into the interconnect. Okay, so let me draw what that means. So let's say I've got some hardware, and I might want to do F1, or sometimes I might want to do F1 prime, a different thing. So I could just, in my hardware, build a mux, and then that goes to some operator G. And maybe there's another input here, F2, goes to G. Okay, so maybe we want G to be a little more flexible, that it can also do different things. So we'll call that G general. Okay, so let me erase this and okay, so this is pretty obvious. I can now do two different F1s, F1 or F1 prime, because I built them both and I put a mux. So my data path is more general. I have some control signal here that controls which one I use. How much more hardware is that going to take? Is that going to be a little bit? It's going to be a lot? What do you think? It depends on what's in each of these. Let's say they're both about the same complexity. Let's say F1 and F1 prime. I don't know, let's say this is like a divide unit, this is like a square root unit, okay? So those are both kind of reasonable amounts of hardware, it's not that small. And then I got a mux. So what do you think? Versus just making F1, how much more expensive do you think it is that I made F1 and F1 prime in this mux? You can't give me a precise answer. Like, it's like a poorly phrased question, I totally agree. So you can't say it's like 1.7 times or something. Is it like 10% more? Is it twice as much? Is it more than twice as much? What do you think? What do you think? Yeah, so I mean, if F1 and F1 prime are about the same complexity, this is going to be actually a bit more than double, because I had to build both of them, and I'm only ever using one or the other. And then muxes actually take, depending on how wide the mux is, they take a reasonable amount of hardware in FPGAs. So If these were pretty big units, then they're probably quite a bit bigger than the mux. So maybe it's 2.1 times, maybe it's 2.2 times as much area. So you kind of really need to want this. Like, this is not a cheap extra flexibility. You basically are only using, essentially, if you take this block, you kind of guaranteed you'll use less than 50% of that block of hardware at any point in time. So sometimes you have to do that, but it's costly. Don't do it if you can avoid it. Okay, the other approach that we can use to make our operators essentially more flexible is, let's say this G that I've been showing over and over again, let's say it was like a quadratic equation. It was like 181x squared plus 78x plus c, okay? Why is it that? I don't know. Let's just say that that's what my system needs. I'm processing some data and I like that. But I come up, one of my signal processing engineers says, well, if we had a little more flexibility, we could change these coefficients. We could adapt to weather conditions in our wireless base station. And so maybe we should make a more general operator where we have these constants and we can actually just send them in, right? So we get some extra inputs to this and we can change A, B, and C. So that will cost us some. The reason it will cost us some is if we actually know these constants at compile time, like when you're running through Quartus or Vivado, the tool will actually build you more limited hardware. It won't build a general multiplier of 180 of something times x squared. It can actually remove some of the logic because it knows exactly what number is there. Okay, so you can get, it's hard to say exactly how much more efficient that is. It depends on exactly what you're doing. Sometimes it's quite a bit more efficient, sometimes it's not much. But basically, the more specific the hardware, you can get some of these extra compile time optimizations. Okay, but this one's going to be more flexible. We can vary it at runtime. I mean, this is not, the change for this particular example from this to this is not going to be as expensive as this approach of muxing. Because we're not going to be more than twice as efficient by changing these, from values that change at runtime and we have to have a general multiplier to being constants. So we'll get something, but it'll be quite a bit less than 2.1x. Okay, so we can do this, but there is a cost, particularly to this approach in FPGAs. Okay, so we try to do as little of it as we can. So that's method one. Okay, so let's say that I'm sometimes doing F1, sometimes doing F1 prime, but it's not changing really quickly. So FPGAs are used a lot in communication systems. So communication systems, usually there's some pick my protocol, maybe pick my channel characteristic, look at my channel characteristics if it's going over a particular copper line or over a wireless channel, and that might choose my communication modulation strategy. And once I pick that, I'm probably not going to change it very often. Maybe I'll change it in a minute, but I'm not going to change it every 12 clock cycles. So if this doesn't change very fast, can you think of any other approaches we could use that might be less costly than just building both pieces of hardware? So what do you think? In an FPGA, now this is now FPGA specific. In an ASIC, this is what you'd have to do. Yeah? Could you say it loudly? Build separate bit files. Okay, so you're saying, we can reprogram the FPGA. It takes a while, but it takes a while. Is like 100 milliseconds to reprogram the whole chip. If I reprogram at 10% of the chip, it's maybe 10 milliseconds. If I only need to change this once every, 10 minutes, hour, that doesn't sound bad, right? So you're right. So the other approach you could have is I don't really need to have both these active at the same time. Just program in one and be able to program in the other if I need it. So swap them in and out in time. And yeah, that is the other approach. So, which is called, so we're reconfiguring part of the FPGA. So usually we call this partial reconfiguration. It's partial reconfiguration because you want to change part of the chip while leaving the rest alone. If you're allowed to just change take the whole system down, then you can just reprogram the whole FPGA. But usually you're not allowed to do that. Because taking the whole, then the whole FPGA goes dead, and actually that usually kills your whole system. So if this is some, cell phone base station or some core router for Cisco, like you just took the whole system out. It has to do a reboot. So that's not a good thing, right? It might be down for 5 minutes, might have dropped like thousands of conversations. So we want to reconfigure this local part of the design, but not break the rest of the design. So what we're doing is maybe we had F1 and F2 feeding our G. And basically, we want to take, 10 milliseconds or so, and change that to F1 prime and F2 feeding G. Okay, so we changed our communication protocol, say. So this is the part of the design that we've changed, right? So F1 changed to F1 prime. So it sounds pretty good, right? Like instead of building both pieces of hardware in here when I'm never going to use them both at the same time, I just build one or the other. What do you think? Is this easy or hard? Yeah, so actually, have any of you tried this? Because you said like hard, like your spinal cord answered that question. Like, which is the right answer. It is actually hard. It's slowly getting easier. So it's getting better than it used to be, but it's still not that easy. So it's done in some applications, but not in most, because it's just a more difficult design flow. Okay, so you guys are right. It's a difficult design problem, or a difficult design flow. But it is gradually getting better. So, okay, so why is this a difficult design flow? Processors do this all the time, right? Like this is how a processor works. You can call a subroutine F1, then you can call a subroutine F1 prime. Just runs different instructions. Nobody worries about that, right? Like you just take that for granted. So that's totally fine. So why is this harder? Yeah.
Continuity. Why is switching the implementation, the rest of the pipeline should be in a safe state to do something that you won't want to do?
Right. So I'm just going to repeat that so everybody here. So essentially, design continuity in time. Like this takes, say, 10 milliseconds. 10 milliseconds is actually a pretty long time, right? Maybe not enough. The end user shouldn't notice it. You could say that's okay. But 10 milliseconds is a lot of clock cycles. So for 10 milliseconds, you're changing this hardware and you haven't thought about what's happening, your system is going to go pretty crazy. 10 milliseconds is what? Probably a few million clock cycles. So if you haven't thought through what happens, the odds that it's all okay through a few million random clock cycles are pretty low, right? The rest of the system has probably been given a lot of crazy data and gone pretty nuts. So yeah, that's one of your problems. So the F1 prime outputs, which are the inputs to G, must do something reasonable. They have to go to reasonable values during this reconfiguration. So, for example, that could be like valid equals 0. So that tagging of our data actually kind of helps us in that we still have to make sure that happens. We have to have a little bit of logic that during the reconfiguration we can force all of the valid bits coming out of this to be 0. But at least that gives us a model of what to do, right? Drive all the valid bits to 0 and all the downstream logic, and drive all the back pressure signals. Let's say there's something going into this. Drive all the back pressure signals saying I'm full, and all the downstream signals saying I'm not valid. And we're kind of hooking into our, what's often, well, what we called a, well, it's often called an elastic pipeline. We're hooking into our handshaking signals to tell the rest of the system, don't take any data from me, don't send any data from me. But we have to make that happen. So we need to put a little bit of extra logic in that detects the reconfiguration and makes that happen. Okay, so that's first problem. And the vendor CAD tools have gradually gotten a bit better at helping you with that too. If you use standard interfaces, then they can actually help you drive these to, kind of these don't pay any attention to me states. So that's the first one. Any other issues? So there are other things that make this challenging. Yeah.
Resource availability or routing?
Yeah. Yeah, so that's a good one. So basically, so resource availability or resource matching. So what do I mean by that? So F1 prime, has to fit in the same space as F1. The idea is I only want to reconfigure part of the chip. I want the rest to keep working. Well, that means that I have to floor plan. I can't let the tools just decide where to put F1 and F1 prime. I'm going to have to floor plan them, so constrain the tools to say both of them have to go in the same spot. And I have to make that spot big enough to have enough resources for whichever one needs more resources of every type. It's got to have enough RAM for the worst one, enough logic for the worst one, etc. Okay, so F1 prime, must fit in the F1 space and resources. Now, I can always make the space bigger, but I guess I got to size it to the worst case of the two, and in kind of every kind of resource. So that's doable, but I've added a little more work to my design process, and I'm going to lose a bit of efficiency from this. Anything else? Any other issues? Okay. Okay, so another one is, here's my G. And the way that F1 connected to G, well, it depends how F1 connected to G. But in traditional FPGA implementations, it connects just with wires, right? It's just all wired together. The programmable routing, we've selected many, many muxes to get the signals from F1 going into G. And whatever fed F1 also is feeding it with a whole bunch of wires. So if I take out this was F1, and I put in F1 prime, it better have the same signals going to G, but it's not just like the same logical signals. I got to use the same wiring. Okay, that's actually a challenging problem for the CAD tool. It not only has to swap a new piece of logic in there, it's got to line all the wiring up so that I get on exactly the right wires when I go to G. Does that make sense? So basically the interface signals, so like the logical interface and the physical wires of F1 and F2 prime must match. Okay, so the CAD tools will help you with this. If you had to, actually early flows for this, pretty much the designer had to go in and make this happen, which kind of drove designers insane, right? Like that's so low level, it's nuts. The CAD tools help a lot with this now. And we'll talk a little more when we get into routing architecture, how they do that, because it turns out this is a more difficult problem for the CAD tools too. They can help automate it, but having several things that can go here that have to hit the exact same wires is tricky. But the vendors have come up with some tricks to make it easier. Okay, so still more difficult, but the CAD tools are helping with this more. And then the last thing, which we already talked about, is that reconfiguration is relatively slow. So I said, for 10% of the device, it's maybe 10 milliseconds. that number is probably changing some from device. You know, it could be made faster if the vendor spent more hardware on it, but that's a reasonable number for most FPGAs. So in some applications, that's limiting. Like if you need to swap back and forth between F1 and F1 prime, you know, every few clock cycles or 100 clock cycles, that's not nearly fast enough. If you need to swap between them every 10 minutes or hour or 12 days, okay, it's okay for that. But it's not fast enough for some things. So a reasonable rule of thumb is it's about 100 milliseconds times the percentage of chip that you're changing. It's never going to be, you know, like a processor changes its instruction every cycle, right? So it can change it 3 billion times a second. Because an FPGA has so many more programming bits than a processor has instruction bits, you're never going to get anywhere near that. Although if they devoted more hardware to it, you know, FPGA vendors could cut this quite a bit. You know, maybe they could cut it from 100 milliseconds to 10, but yeah, they can't cut it to like 300 picoseconds, which is like a clock period. Let's see. Okay, so that's it for that programming model. Yeah?
With all the difficulties, why would anyone choose Network 2?
Well, it is more efficient. So it's tempting. So academic researchers love it because it's kind of intriguing. And if you can make it work well, it's more efficient. And grad students are, you know, you can make them do a lot of things that like professional, working engineers might balk at it for a while. So I remember one researcher at Brigham Young University did a lot of research in partial reconfiguration. And he was doing it before when the CAD tools were significantly worse at this. So in one of his presentations, he had this GPR. That was the tool he was using to do the place and route. So all over the place, he had GPR. So at the end of his presentation, I asked him, what is GPR? And he said, that's graduate student place and route, right? So he had a team of graduate students that were just doing it by hand, right? Now, it has gotten better since then. When I was at Altera, for many years, Altera couldn't do partial reconfiguration, largely for patent reasons. Xilinx had a patent on an SRAM cell technique that Altera couldn't violate. Ultimately, that patent was cross-licensed, then they could do it. And we put the hardware in to be able to do this. The key reason for it was actually the communication market. So there were some pretty big customers that were putting systems into core routers. So core routers are things like Rogers has a core router that is going to take all sorts of traffic from all over Toronto, multiplex it together, change the protocols, like convert it to like SONET protocols, which are ones that go over optical fibers halfway across North America at really high rate, all muxed together, and they get taken out on the other side. Okay, so those core routers are bringing in tons of channels from all sorts of protocols like DSL and local fiber optics, and then converting them, muxing them together, converting them to various SONET protocols. And it turns out that, you know, Rogers has sold bandwidth to, you know, smaller internet service providers, big businesses, et cetera. And they connect into those core routers with different protocols. So you might have a certain DSL, and then maybe your competitor uses a low-speed fiber optic and so on. So they'd have to build in their FPGA designs. I mean, Rogers wouldn't build it. They'd buy it from companies like Cisco. But they'd have to build into their designs essentially all the input protocols you might want across many channels, and then the various output protocols. But you know they're never all going to be used at once. So being able to reconfigure the device to take out one of them and put a different one in allows you to have a much more efficient device. And these are pretty high-end, expensive systems, so they're willing to go through a fair amount of effort for it. So that was the killer app that made us put it in. Other people could use it too, but those are the ones we're really focused on. And they don't have to do it very often. They basically somebody just doesn't want as much bandwidth, so they cut their allocation this month, and they want to resell it to somebody else who uses a different protocol. And they can't just reconfigure all the FPGAs in the whole system because that takes their core router down. So, and you might have heard that Rogers had some problems with taking the internet down for everybody makes people annoyed, right? So So yeah, it wasn't like an option to, now they wouldn't take it down for a whole day, but even if they say, well, we're just going to reconfigure the FPGA, reboot the system, and everybody loses internet for 10 minutes, but that's okay, just go for a walk. Like they're really not okay with that. These core routers have like these incredible service agreements of like no more than 5 minutes downtime in a year and so on. Like that's the contract you have. So if you say I'm going to reboot it and it's going to take 10 minutes, it's like you've already blown your yearly contract and you're refunding things to people. So they would, yeah, their alternative was just basically build in all sorts of protocols that they know they're not going to use all at once, or go through the pain of this and try to be able to mux them on top of each other. And a bunch of those core router vendors did go through the pain. Does that make sense? I mean, this is getting ahead of myself too, but one of the things we'll talk about later in the course is the latest FPGAs are also starting to embed hard networks on chip in an FPGA. That provides a new abstraction level that is above these low-level wires, and that actually potentially is going to make this a lot easier. Okay, so part of what makes this hard is the very low abstraction level of we connect things with raw wires, and the latest FPGAs have some different options for system-level interconnect between big things that is a bit higher level that can make this easier. But that's kind of a digression. I'll talk about it later. Anyway, a good question though. So, okay, so let's see. Let's see if I have any time for this. Okay, I don't think I have any more time for this, but we'll talk about at the start of the next lecture. We talked about basically all the streaming models we want. I'll talk about some streaming optimizations, which we've already kind of talked about, pipelining. We'll talk about a few more. And then we'll go into some other models that are not streaming. Okay, thanks everybody.